Hello everyone, I'm Prajit. I'm excited to present Quantum Whisper, a quantum cryptography demonstration that brings the BB84 quantum key distribution protocol to your website. This project showcases how quantum mechanics can revolutionize secure communication by creating unbreakable encryption keys. What makes this special is that we have made complex quantum concepts accessible through an interactive web application that anyone can use without specialized hardware. Let me show you how quantum cryptography works with this application. So the quantum whisper has two main components: quantum key exchange and encrypted messaging. The key exchange implements the famous BB84 protocol, the first quantum cryptography protocol ever developed. Here, two parties traditionally establish a shared secret key that's protected by the laws of quantum physics. Once they have matching keys, they can use our encryption system to send perfectly secure messages using AES 256 encryption with their quantum derived keys. Let me show you how the quantum key exchange process works. So I'll just reset all this. So in the step 1, we generate the quantum key. Let me click generate key. You can change the key length. I'll just go with 32 bits. Um, so for the here we can see we have three main components: random bits, measurement bases, and quantum states. For the random bits, let's say we have a user called Alice. Alice starts with the random classical bits. You can see zeros and ones here. These represent the information she want to encode with, and this is the measurement base. Here we have z's and x labels. These are quantum measurement bases. So for example, z basis uses the standard 0 or 1 state, the quantum mechanics, and while x basis uses the superposition state plus or minus. And the quantum state, here you can see the symbols like 0, 1, plus, minus. These represent the actual quantum states. So Alice encodes each bit using randomly chosen bases, and creating this creates the quantum particle with specific state properties. So this shows which bits will survive the quantum protocol. Um, so these become the final shared key after Alice and Bob will see that here. Compare their measurement choices. So this is the essence of our quantum mechanics, which is information encoded in quantum state that can only be measured only once. So for the step 2, we go for Bob's. Let's say step 2 is getting the quantum key that we generated. Let's say the user that does this is Bob. Bob independently chooses. I'll just copy the quantum key here, paste it, or you can download the sound of the quantum key. So this is 19. So this is just GG waves technography to encrypt the audio to have additional security, and I'll upload the sound. So 25 right here. For additional security, we'll just copy and paste the key which is generated here. So this is the key that Bob and Alice will compare. You don't have to generate the sound to do this. We can just copy the quantum key and paste the payload. We'll just generate another combination. Here Bob here Bob uh, independently chooses here Bob independently chooses random measurement bases completely separate from Alice's choices. He has no idea which basis Alice would choose for each qubit, right? Uh, for Bob's measurements, when Bob measures each quantum state, this gives us a crucial property. If his basis matches Alice, he gets the correct bit. If the bases differ, he gets a random result that is 50% right. So if you look at the comparison, only when Alice and Bob use the same basis, they get the matching bits. These matching bits become their shared secret key. So this is called basis reconciliation. This is where they publicly share which basis they used and keep only the bits their bases matched. Here the matching indices are found here. So why we do this is that if we have an eavesdropper, he can't benefit from this information because they would need to have measured the quantum states correctly in the first place. This is why quantum cryptography is hard to break. So since the quantum key is matched, now we can go and perform the encrypted messaging. Here we can see the key matched secure status. If we, let's say we didn't correctly give the key here, I'm just randomly selecting a key different from the one here, and then I'll just go ahead and copy and paste the data key here. Here it will show mismatch, and you key avail it won't, you can't decrypt here. Let's say I'll just write my name, encrypt, copy and paste the message here. It won't work, the decryption will fail. Only when we have the right quantum key that we generated here and verified here, the quantum key is validated and it is matched, then we can have a right encryption and decryption mechanism. So I'll just encrypt and copy the encrypt message and then give it to the decryption system, and then I'll just decrypt. Yeah, so we can use this as a basic chat. So I'll just write another message. Yeah, I'll just build a basic chat application here. um, that's about it for the demonstration, and I'll just talk about key technical implementations. um, So this is quantum simulator. This contains our BB84 protocol implementation, which is very close to the actual implementation. Um, here we have main functions like run BB84 and measure quantum state, which simulates the real quantum physics. We have GG wrapper. This handles audio encodings of quantum keys into downloadable WAV files, making the key portable between devices easy and secure. And for our quantum React hook, I did use encryption hooks. This is our custom React hook that manages AES 256 encryption with quantum derived keys. um, and finally we have quantum context. This is the state that this is a quantum state across our entire application, ensuring key synchronization between Alice and Bob. So the entire system is built with React 19, which uses modern cryptographic libraries and can use in any web browser without special hardware. So yeah, thank you for watching this demonstration for quantum cryptography in action. Quantum Whisper is deployed live at the link in my GitHub as well as in dev post. And yeah, thank you so much for this opportunity.